We tend to think of math as this, like, totally fixed thing, right? Like 2 plus 2, it's always going to be 4. But what we're really digging into today is how all these mathematical truths, how they even become truths in the first place. And you've given us some seriously interesting stuff about math history, and let me tell you, well, it's not a straight line, that's for sure.
Yeah, it really is amazing how math has been like built up piece by piece over centuries. Each mathematician, each time period, they're building on what came before. But sometimes it takes some pretty wild turns along the way.
I know, right? So we've got this classic history book by W. Rouse Ball. Then there's this collection of papers all about how mathematical analysis developed between the 17th and 19th centuries. And get this, a whole report on like teaching math from the 1960s. It's kind of mind-blowing how much history is packed into the math we learn.
Oh, totally. And I think instead of just going like step by step through a timeline, we can find some seriously cool links between all these different sources.
For sure. Okay, so I found something in that history book by Ball, this ancient Greek problem. They called it duplicating the cube. And before you think we're talking about like photocopying a 3D shape or something, this is way tougher.
Oh yeah, this one really stumped them. See, the Greeks, they wanted to make a cube that had double the volume of another cube, but they could only use a straight edge and a compass.
Mm.
Sounds easy, maybe. But this problem, it puzzled mathematicians for centuries. We're talking big names like Hippocrates.
Wait, not the Hippocrates, like with the doctor's oath?
Nope, not that one. But even Plato. Even Plato was interested in this problem.
Plato? You mean the Plato, the philosopher? Never pictured him as a like geometry whiz.
It's easy to forget, right? The ancient Greeks, they didn't separate subjects like we do now. Math, especially geometry, that was like key to understanding the universe for them.
So, like, if you were Plato trying to figure out reality and all that, a problem like this will only be irresistible, huh?
Exactly. It wasn't just about doubling some cube. It was pushing the very edge of what they knew about math, about everything. And this one problem, it led to some huge breakthroughs in how they thought about geometry. Like they had to invent new tools, new concepts, things like conic sections.
Conic section.
Yeah, like if you slice a cone at different angles, you get these curves. That's conic sections. And they had to dive deep into ratios and proportions, all because they wanted to figure out how to double that darn cube.
That's wild. One little puzzle and it changed so much.
It really goes to show, sometimes these super specific problems, they're what spark the biggest breakthroughs. And Ball's book, it's got a few more examples like trying to cut an angle into 3 equal parts.
Oh, like perfectly.
Exactly, trisecting an angle, they called it. Or how about squaring a circle? Couldn't do it with just a straight edge and compass either. These things, they really push geometry in ways nobody expected.
Makes you wonder what math problems are driving mathematicians crazy today that'll lead to, like, the next big thing, right?
And speaking of big things, I gotta say, I was so into this story about Gerbert. He was this scholar back in the 10th century, totally revolutionized how math was taught in Europe. His story in Boll's book, man, it's something else.
Oh, Gerbert, he's a great example of how math history doesn't always follow a straight line. Started from really humble beginnings. This guy ended up as Pope Sylvester II, but math, that was his real passion.
And talk about good timing. So
Hmm.
Europe back then, they'd kind of lost a lot of math knowledge, right? And here comes Gerber bringing back all this crucial stuff from the Arab world. Like he brought back Arabic numerals.
Which we just take for granted. But can you imagine going back to Roman numerals?
Oh man, no way.
Right, Arabic numerals, those were a game changer. Made calculating so much easier. And don't forget the abacus. I know it seems kind of basic now, but that thing was essential for so long. It really makes you think, like, how much progress in math depends on the tools we use, how we write numbers, how we calculate, all of it.
It's like looking at computers today and all our algorithms. We wouldn't be here without those earlier innovations, right?
Totally, it's all connected. And speaking of upheavals and changing how we do math, this collection of academic papers, conflicts between generalization, rigor, and intuition, it takes us to 19th century Berlin. Seems like there was another lesser-known figure shaking things up.
Ah, you must mean Johann Georg Strauss. Not as famous as some of the others, but his work. He was focused on something really fundamental. Continuity.
Continuity.
Yep, he was researching continuous functions, and here's the thing. He was doing it at the same time as some other way more famous mathematicians, and they were all grappling with similar ideas.
Like some kind of hidden network of math minds all tuned in to the same wavelength.
It just shows you discovery, it's not a straight line, it's a web. All these ideas,
Yeah.
interconnected, being explored from every angle. Makes you wonder, what if someone like Tralles, what if he'd gotten more recognition back then? How would math be different today?
It really is mind-blowing, isn't it? Like, what if trellis had gotten more attention? How could things be different now? It's like, it makes you realize that math, it's not just about the big names, right?
Exactly. And it brings us to a concept that's, well, it's messed with mathematicians for centuries. Infinity.
Yeah, infinity. That one's a brain twister for sure.
It really is. Even for mathematicians, it stretches our intuition to the limit. It's not hard to see why it's got such a, shall we say, dramatic history.
Our collection of papers, Conflicts Between Generalization, Rigor, and Intuition, they really dive into one of the big debates about infinity. And it all goes back to, like, calculus in the 17th and 18th centuries, right?
Right. So you got these brilliant minds, Leibniz, Newton. They're laying the groundwork for calculus,
Right.
but they're working with these things called infinitesimals.
Infinitesimals. Okay, break that down for me.
Basically, imagine something smaller than any number you can think of, like these infinitely tiny pieces of a whole.
Whoa. So not just giant numbers, we're talking crazy small, too.
Exactly. And it revolutionized things. They can model motion, change, all sorts of things in ways they never could before. But some mathematicians, they weren't so comfortable.
Oh, how come?
Because, well, how do you really handle these infinitesimals? It wasn't super clear how to do it rigorously, like building a mansion on, I don't know, stilts. It just wasn't rock solid.
So that's where the conflict comes in, right? Trying to shore up those foundations.
That's it. In the 19th century, there's this big push for making math more rigorous, super precise. And one of the big players in this was Augustin Louis Cauchy.
Cauchy, yeah.
He's the one who basically tried to wrangle those infinitesimals. He wanted to give calculus a stronger base, something more solid, using the concept of limits.
Now, Cauchy's work was a big deal, but I'm guessing not everyone was on board.
Oh, you better believe there was pushback. This wasn't just about definitions. This was about what math is at its core. On one side, you had Cauchy and his camp, all about rigor, logic, every statement proven without a doubt. But then you had others, like Dirichlet, also in those conflicts papers.
Dirichlet, right.
He said, sure, rigor is important, but don't forget intuition. That spark, that creative leap, that's how we discover new things. You can't be so focused on being perfect that you miss the breakthroughs.
It's like you need the balance, yeah.
Yeah.
Solid reasoning, but open to those flashes of insight.
Exactly. Dirichlet even said that Cauchy's limits, while they made sense logically, they were maybe too restrictive. They might miss cases that intuitively just felt continuous.
So even something like rigor, which seems so basic to math, it's not so simple, is it? It wasn't about right or wrong, it was about different ways of seeing things.
Absolutely. This whole debate, it highlights something crucial about math. It's not some statue, fixed and unchanging. It's alive. It's this conversation, always going back and forth, rigor and intuition, general ideas and specific examples. Finding that sweet spot between logic and possibility, that's the key.
It really makes you think, if those math giants couldn't agree about something as fundamental as infinity, how can we be sure we've got it figured out?
Right. It's a question people have been asking forever. And it brings us to something really interesting. How do we pass on what we do know? How does teaching math, how does that evolve? And that's where our third source comes in, that report on math education from the 60s.
Yeah. That report, it's like a snapshot of a big shift in how we teach math, the new math movement. Lots of debate back then about what to teach, how to teach it, right?
Oh, definitely. People were starting to realize that the old way, memorizing formulas without really understanding, it wasn't working. New math, that was all about going deeper, understanding the concepts behind the math. Things like set theory, abstract algebra.
It's like we're still figuring it out, aren't we? How to make math, like, click for people, but also keep it, real math.
It's a tough one. And this report, it shows how these debates, they just keep coming back around. That push for deeper understanding, getting to the why behind the numbers, that's something people are always wrestling with.
And they were really focused on some key things back then, like understanding how things are related, those functional relationships, and the beauty of simple formulas, how elegant they can be, and of course, just being able to do the math, that numerical computation. Seems like even with computers now, that basic stuff still matters.
Totally. Tech is amazing, don't get me wrong, but it's built on those math principles, right?
Yeah.
If we don't get that, we just become button pushers, no clue what's really going on.
It makes you think about those guys, Gerbert with his Arabic numerals, or those mathematicians going nuts trying to double their cube.
Yeah.
They didn't have calculators and all that. They had to understand the math itself. And look what they did.
Exactly. It kind of makes you wonder, what about the tools we rely on so much? Will they last? Or will future folks look back and be like, how'd they ever get by with that?
It's humbling, right? Our understanding of math, it Never stops evolving. Always something more to learn, some new way to see things.
And it makes those figures, like Gerbert, Tralles, even more amazing.
Huh?
Pioneers grappling with these huge ideas shaping how math evolved. If they're not so well known now, who else is out there? How many brilliant minds hidden in history?
Like, we stumbled into a secret library full of these amazing math stories, debates, breakthroughs, stuff most people never even hear about.
And that's the magic of a deep dive like this, right? Math isn't just some rule book. It's a story. Human ingenuity, the struggle, and then that aha moment.
Mhm.
Even the toughest stuff, it all started somewhere.
So, to everyone listening, if you take one thing away from this, let it be that sense of wonder. Math isn't about memorizing, it's about exploring, challenging what you think you know, finding that elegance behind it all. It's pretty amazing when you think about it.
And this was just the beginning. These sources, they're like jumping off points. There's a whole universe of math history out there to discover.
Who knows, maybe you'll be the one to rediscover a forgotten genius or spark a whole new debate about infinity. Thanks for exploring with us.